Okay, thank you very much for the introduction, and thank you to the organizers for giving me the chance to talk a little bit about the different fields, and that is digitalization of materials research. If you start with an image like this, you see the world from outside the world. First picture taken from Earth in 1968 with Apollo 11, it showed that little planet with a dark background. Now why do I show 1 3/4 of Earth? That's the footprint we, as human beings, keep on that Earth, or that's the number of Earths we would need. And that's too much. That's not sustainable. So you can imagine that this may be a neural network, and that represents the digitalization. And the question is, can we use digitalization in our materials research, in our efforts altogether, to get back to one world consumption of everything? You've seen this slide before from my colleague Alexander. So we have different fields, from technology to policy, and from efficiency to sufficiency. And my part is the connecting part, the red dots, the digitalization, the digital information, and some applications, what we do in materials research. The previous speaker gave you a good impression how important simulation is for a better understanding and also for a better design for a given application, and the materials need to fulfill that. So testing is a major part of it. My background is codes and paintings, so when it comes to composite, we share kind of the polymer basis, but we do different things. However, for about 10 years now, and I'm pretty sure you heard about DSF, the big players in the field started using optimization and digitalization when they screen their materials. Why do they do it? You capture now all the information. You think of an electronic lab notebook. Everything you do is captured in the digital world. It's connected to what you've done and how you have done it, and it allows you to retrieve the information, and ultimately, with the advent of AI, you can build models and use these models as co-workers. Now what needs to change, and I guess as students you're all too familiar with it, is the trial and error approach. Very often you have a great idea, you run to the lab, you do some testing, you're not really happy with the results, and you think a little bit more, and so on and so forth. It's taking a lot of time, and when I've been a student myself, you tend to not write down everything. You tend to forget, how did I do this? And then you have to repeat that. If you are to use digital efforts in your development, you need to change the approach a little bit. So look at this here. What does it show? It shows the human being kind of being outside of the development process. It's the thinking part here that needs to be done before you start the experiments. And tightly connected, so to speak, woven in with the experiments, are generating results from the experiments, and then exchange this until you are happy with the final outcome. This is called digital chemistry. The term was coined maybe 5-6 years ago. I read a report from the Royal Society of Chemistry back from 2020, and they were giving you a number of ideas what digitalization needs. And one of the low-hanging fruits in the business is shown here to the left, or my right. This is a typical experiment, and the first thing to improve the situation, to go more digital, is to connect everything to controllers, to retrieve data, to use automation wherever possible. So the cycle kind of changes a little bit. You really have to study hard, read the literature, know what's going on, and then come up with ideas what you want to do. You may have to think about or leads into experimentation, think about, can I do more automation, helping me in the execution? Then carefully think about analysis, not just do the experiments, but always think about, what have I learned? Do I have a set of objective data helping me to understand what's going on, and then combine both to iteratively, so in very few iterations, improve your results. Another part, and then I'm stopping with the chemistry a little bit, is that you cannot do everything. The network I showed initially also means a network of institutions. That's not only a network within India or within the city and within the college. That, in the long run, needs to be a network worldwide, a global network. In one of the projects called War from the Imperial College, they had set up an analytical lab, and then they called it dialer molecule. So if researchers elsewhere did their research and they needed to have some analytical results, they basically connected via digital communication with the experts on the machine, sent in their samples, and got results from the experts. What are we doing at our university? How do I blend in textile is more the question. Well, my background is physics. I'm in the electrical and applied informatics department, so I'm responsible for the digital part of the lab. I work closely with colleagues in the chemistry department, and you see their reputation by some front covers from their research results. And we founded at the university an institute called TIT, so Institute for Surface Technology, where we try to go the next step using digitalization and automation to drive and thrive in the coating chemistry. So that's our mission. Accelerate the research on one side, but also advance education. It's not a given that students, shown here, familiar in the lab, automatically know how to use and work with robots. That's kind of a cultural change, and it takes some time to do that. This is a fairly large investment from our university. I'm talking about $3.5 million just for the equipment, into a system that automatically formulates, applies, and characterizes coatings. And we already started adding things such as lasers and microscope to carefully investigate the structures. We developed surface testing tools, automated or textile coating tools. To give you an idea what this machine is doing, well, it does what humans do. It builds a formulation, it applies the formulation via spray coating, it tests the formulation, and it stores the samples. And every single step along the way is documented digitally. So if you go back even a year later and say, what did I do with this sample that was so great, you have a full set of your process. One of the important things in coating chemistry is seeing things. Is that quality good? Do I get what I was hoping for? So, and seeing and testing goes hand in hand. If you scratch the surface, if you want to check for chemical resistance, you apply something to the surface, and after some time or even time resolved, you look at it. You can build these machines by yourself, but you can also complement it with tools from the production industry called machine vision. So, how is our process working? Well, when we talk about coatings and paintings, we have a set of raw materials which we can use to tune, to optimize the specific coating for a given application. And instead of heavily relying on the expert, we only initially rely on his input, giving us a selection of these raw materials, but then start making formulations guided by an intelligent design of experiment. The way it works is you need to identify all your input parameters. This can be the material, the amount of the material, the process time, or whatever is important from this process. And it correlates all these inputs with the qualities you're interested in, with adhesion, scratch resistant, chemical resistant, color, you name it. The algorithm is your companion in this journey. The way he works, or it works, is the Gaussian process, and it's iteratively improving its knowledge by building a neural network. To give you an idea what these algorithms are capable of, you see the movie running in the back. It's kind of like a pudding type formulation, a non-Newtonian liquid, and it's quite challenging to dose a certain amount in the shortest time possible. And we had the algorithm control this machine and gave it the simple task of learn how to dose as precise as possible in the shortest amount of time. And then we just said, go ahead and do it. And so this iteration, this optimization was entirely done by machine learning. The algorithm needed to learn something, and the parameters here were the weight and the time. It optimized both parameters satisfactorily. Now, giving you an example of what we do with textiles. We have an application machine from a company called SM Coating, and the idea behind is that we use recycled polymers, leftovers so to speak, and use them to coat, add the functionality to the surface. It's kind of a melting process. You can also think of using UV curing, so this is a flexible tool. That's generally the scheme, is to have modularity in your equipment. And as expected, when you start somewhere, you get clogging of everything. The coating is not a sugar coating, but it's more like clogging the surface coating. And over time, we developed a process or a set of process parameters that we finally got just the sugar coating of the fibers, and the particles in there should act as a catalytic center of sort. So that was the application behind. When we do projects, normally we do it together with industry. So this was together with a company called Polis in the Netherlands, and they were interested in making functional coatings, curtains basically. I talked about imaging and testing. So when you make a surface, it's shiny, it's glossy, it's perfect. You do some mechanical treatment like scratching it in a periodic manner with a defined force with different surfaces. You change the gloss and you look at it and you kind of correlate, oh, I can do 100 strokes and the gloss changes by that much. The result of that is you build a model first and try to correlate this information and then use the model to predict how it will change. And then you change the parameters of your formulation and see if you can improve the gloss or the resistance to scratch. You can also teach the algorithm to look for typical defects. You apply a coating and you cure it, you often have air bubbles or craters, imperfection in your polymerization or drying process. And you can teach the algorithm to look at these defects, identify them automatically, and then correlate it to the process parameters so that you can avoid it in the future. When I talk about algorithm, just towards the short side step, when you talk about algorithm, it is the big thing of image recognition. We all know automotive industry tries to have autonomous driving with the help of cameras and learn situations basically. It's similar here, if you look at the number 3 and you take this image, this two-dimensional pixel information, and you correlate it to a one-dimensional vector, and you have a number of neural layers in between. The idea is that you correlate your input vector to some number you want to interpret as 3 in this case. We have a vague guess how humans associate these images. For example, You know, if you are human, you may think of a line as an O and a line or so. But we have no idea how this neural layer from the algorithms interprets inputs and comes up with the result. However, we know the mechanism is still defined. The mechanism is basically defining an error function. So taking all the inputs here and calculating their way to a particular neuron, and you do that for the entire set of connections. And then you sum up all the Rayleigh factors, and you take sigmoid or Rayleigh functions to weigh them. And that's the learning part. So if you think of the math behind, you have matrix multiplication, and you continuously do that until you have it optimized. I'm not a mathematician, so I will know exactly how they do it, but you all know linear regression, and that's in a similar way trying to minimize this loss function. And then in the end, you have all these hidden layers, the weighting factors, that allows you to look at the input pixel array and determine, oh, that's number 3. You can also apply this concept to color detection. One of the challenges in our industry is to predict from a wet color measurement how the dry color will look like. The reason why it's a challenge is it's quickly, but then applying and drying is time and cost intensive. So if I can make a model on the liquid color, I'm saving these steps and I can make a faster process. We use these algorithms in several batches, trying to develop a model to predict from wet color the dry color. When I say we have a funded project together with industry and colleagues from the chemistry department as well as the computer science and electrical engineering. And as a university, you don't have always an entire machine to start from, but you have individual components. That is, say, the electronic lab notebook from the human part of it, doing some work in the lab where we don't have automated solutions. And you need to link all this information together so it's not lost and you can find it in what we call a database later on. And on top of everything, you also need to connect the machine learning algorithm to do this, to retrieve data and to understand what's going on. This is a tedious task. Simply the fact that you talk to the equipment manufacturer and ask him to lay open the code or the format of his data can be a challenge. Going back to the color measurement, one of the challenges here is that you have, of course, changes in your spectral behavior. So think of making an iteration, a simulation of this curve. You have a lot of data points with hardly any change and only a few data points with big changes. That requires some adjustment of the algorithm. So there is not a algorithm solving it all. We need to go back to the math drawing board. There are software packages like Python. There's software available for free like TensorFlow who will do the math for you. So you don't have to program that part. However, input data and what you learn from it, that's your responsibility. The good news is the technology has evolved quite a bit. So if you now do, for example, image recognition, you can think of a spectrum also as a one-dimensional image. Just don't look to the pixel of an image information, but look to the number, whatever reflectivity you have as a function of wavelength, as an input vector. And so you find something, for example, like the UNet, which basically condenses the hidden layer to a very easy, mathematically quickly executed system, and then has a procedure to decode it and then come back with interpreted images. So all you need to do is build the very first top layer where you have to teach with a moderate amount of samples what you are interested in, what your specific task is, in this case, the image of a color. And the result is very impressive. So the blue curve here is the wet color measurement, and the green curve is the measured dry color, and the orange curve is the measured or the predicted dry color from measured wet color. And that is a very good result. We also do that for other parts of chemistry, for example, solubility. That's a big challenge, and in this case we work with a company, and let me assure you it was not an easy coming together, because they have a human expert, having seen hundreds, and if not thousands or 10,000s of flasks with dissolved polymers, and for him it was clear, it's whatever the grade is. For the photo and for the image recognition, it was not. I had to learn that. And in order to learn something, we had to build a robotical system that takes images under very defined situations. If you don't have that, you cannot really derive these good images. So automation is a necessary part in that business. Give you another example where we employ these technologies. We had a customer who has a product in the market, and the market requires more bio-based, more sustainable solutions. So the customer had this, and we wanted that green label. That label you only get when you have 60% of your ingredients being materials that are renewable. So you want to have that sticker, and you have a long laundry list of materials and processes and properties to correlate. It's not that simple that you take one, throw the other out and say, now it's working. It's an iterative process. And what we have done is we identified the binder as the critical part. We had 3 alternative binders from renewable materials, and we used the algorithms in 4 batches of 15 samples each to converge to only one solution, that number 3 here. And the algorithm gives us a pretty good model. So the model is the data points, and the mass, the model shown is a curve connected by the data points. The important part is that you also get an quote-unquote interpretation or an opportunity to interpret the numbers with the chemist eye. The algorithm only identifies for a certain property, these are the critical parameters. And the chemist will then say, oh, it makes a lot of sense that, say, the water resistance is driven by the choice of binder. This correlates the world of math to the world of chemistry, and this is a major factor in the acceptance of this technology for chemists. So what we believe is that the old-fashioned way of having a great idea, running on experiments and iteratively with trial and error come to, at some point, good results, can be streamlined, can be optimized by setting up the experiments nicely. That requires actually either you become not only materials experts but also data scientists and maybe have an idea what the market looks for. You work with a team of experts and setting up the experiments using automation as much as possible. And then you get something for free. The mathematical model becomes your digital partner, your digital co-worker, because it captures the correlation from your materials and the final product. This example I would like to just share briefly with you is where we get funding from these days. So this is from a program called Green Tech from the Ministry of Environment, basically, and they support using digital technologies in materials research. And we have 4 companies, 2 research institutions, who work together to develop a more sustainable product for one of the partners, using automation, using advanced sensors and data sciences. The challenge, and we are in the middle of this project, so far was to get everybody behind the concept. So we are 1.5 years in the process, and we finally have the data scientists setting the stage so that everybody knows what to contribute and how we will fill the database in the future. The last thing, and then I'm done with my presentation, is a project where we also concentrate or focus on the human aspect in that process. So we call it SMIL project, Smart Interfaces, and the idea is, like I've shown before, taking some sort of recycled material, add functional coatings, think about the power consumption in your processes, think about the usability, the ultimate performance in the end, so let's say washing cycles, and then collect all of it in the knowledge base in our data pool. The factor here to consider is that yes, we try to make it a circle, thinking of circularity here, but we also have to learn as faculty that there are students involved that we trained in one direction and that we have to retrain now a little bit in a new direction. And that's a tedious task, and I'm pretty sure that Monica will explain a little bit more about it. So I've added a final slide from the Center of Excellence in our state, run basically by the ITA, Institute for Textile Technology in Aachen. And that is, if you want to go into a new technology, and I look to the digital part as a new technology to the textile industry, then it's not something you learn in a book or from a book. It's something you need to actively participate in, you need to get yourself immersed into. You will not be able to do it alone. You have to work together with experts from different fields, so that in the long run, textile will be interlinked in a more interdisciplinary than this way holistic approach. Thank you for your attention. Of course, if you have any questions, let me know. Go ahead.
I have faced personally also this thing during my MTech program in AI. When we used to go for a project for which I know the subject, the data set availability always has been a question. Where you suggest that where we can enroll, or from where we can get which data which can be subject to analysis and AI model training?
That is a very tricky part, simply because when you work with industry, which we very often do, they don't share data. I mentioned BASF for a reason. They buy their supercomputer, they run their supercomputer because they don't want to share data. As a researcher in a public institution, I'm more than happy to share my data. I should publish, right? But I very often have not the complete set of data, especially the one that failed. This is where the algorithms learn the most. And so I need to establish, maybe you heard the term electronic lab notebook. I need to establish that as a good habit for my future lab work. Then I have the data I generate. I have to convince my friends in other institutions to also share into that pool. And over time, it's not something you can buy off a shelf somewhere right now. But you have to start somewhere. And we have a wealth of data. When you saw Alexander's talk with a wealth of process data, and that needs to be captured digitally so that we can utilize it for further development.
Thank you.
So, do we have any more questions? So they have understood it.
Oh, great. Then we can take the test.
So, thank you, sir. It was in fact a quite interesting presentation on where sir talked about sustainable aspects in textile processing. So, moving ahead with the technical session 2, we have another dynamic speaker among us, Professor Dr. Monica Evans-Stetter. So, she'll be talking on twin transition, greeting of and by digitization, a competency framework transformation management. Ma'am, please. mic. Oh, very low. Can you put it down a bit? Yes. So, distinguished guests, ladies and gentlemen, it's an honor and a pleasure to be here. And I want to give you some insights on an ongoing work in progress, on twin transition. I call it Challenge of the Future. And it is related to the lecture of Professor Joost. It is not working. Ah, this is it. Okay. Oh. Oh. I'm connected to this network, which was already introduced, and I'm from the management side. And let's talk about sustainability, as nearly everyone has. But I have a different picture. So these are the planetary boundaries, and 6 of 9 of these planetary boundaries have also been crossed. So, did you ever hear about the planetary boundaries? And the people who already heard about it show up? Okay, my colleagues, but no one else. I take it this way. Thank you. And so the planetary boundaries is a concept of the Swedish Stockholm Institute where they try to give us a compass in which is the to give us a compass.
We can hear you.
Okay, now I have to be louder. Okay, so sorry. I don't want to fulfill the stereotypes of women in technique. It's shaming for me. Okay, the planetary boundaries are like a compass, and it's not only climate change make us anxious, but to look at that we have these 9 fields, and you see that, for example, the biosphere integrity is already very red and hurt. So we have lost, for example, in Germany, 70% of our insects. It is, and many animals are extinguishing it these days. Or think about the novel entities. You, as textile engineers, you should know about the POPs, and the POPs are accumulating as forever chemicals causing cancer, and this is one of the new novel entities. So we have a lot of things to do to act sustainable. And to act sustainable, the idea is that we have the sustainable development goals which guide us into that direction. So it does not mean not to produce maybe POPs, but only that way where we really need it, and to protect the people with decent work, for example, while they are using it. So, one answer of, tell me what is going on here. One answer of the Sustainable Development Goals is the Green Deal of the European Union. And you see just a bunch of regulations which are all related to sustainability somehow. For example, at the left side, you have something with waste management, renewable energy, carbon border adjustment mechanism. The carbon border adjustment mechanism tells us that in future, every product which is coming into the European Union will have a carbon footprint, and along the carbon footprint, you have to pay taxes.
at the border coming in Europe. Yeah? So they want to force, Europe wants to force the production countries to think about climate change and sustainability. And one of the innovations related to that is the digital product passport, which is a digital twin, for example. But not only sustainability in the ecological context is important, but we are talking also a lot about human rights, occupational safety and health, due diligence, and also that has to be followed. So one of the biggest framework is the framework on circular economy, and we have also a framework on textiles, which is then integrated in the so-called eco-design regulation. Is there any technical help? I think I need to see my slides. Something has happened here, and I cannot see the slides here on the screen anymore. As I told you about the digital product passport, it should be invented already 2026 for the textile. For the batteries, it is already in use. And so you have a digital twin on which is along the whole supply chain. You see that from Q2, Q1, producer, distributor, customer, recycler. And you have, for example, with a QR code, you can read it and see how many water, chemicals, whatever, have been used, also which certificates have been used, and it is also integrated how you can repair or maintenance or dispose the product, and how you should do that, and how you should treat the product to keep it as long as possible in use. So think about the amount of data which you have to collect in future to bring in a product in the European Union. So you have to immediately start to collect all the data along the processes related to the product. And if you think about how many products you have to print on one machine, for example, then you have to make a lot of calculations too, and you will use artificial intelligence to integrate the data collection which you need for your digital product passport. So I already talked about that, for example, carbon footprint, environmental footprint. What I forgot is, for example, microplastic release. Emissions to air, water, soil, amount of waste generated, including plastic waste, and amount of hazardous waste generated. So it's really, really differentiated, and we should prepare for that. What I also want to include in the context of this sustainability is the human rights due diligence. Germany has already in 2021 already started with this Human Rights Due Diligence Act, so it was valid, and since that time the companies, over 500, over 1,000 employees, try to get data about their suppliers and about the human rights. So they're asking the suppliers, how do you behave, for example, in gender equality? How do you behave in occupational safety and health? How many accidents do you have? How are the people treated at the workplace? Do you have contracted and non-contracted people? Are they terminated? How are the training programs? And so on, and so on. What they will do, what is behind that, is a risk-based approach of risk management. So the brands in Germany estimate how dangerous it is to work with you. and they have to show that they have done anything to convince you to do better, that there will be no human rights violations, and so these two things in mind before I continue now with digitalization. So this is the one part, sustainability, where we have to think about. And the second part of the twin is the digitalization. Twin transition means digitalization and sustainability thought together. And let us have a short look on the possibilities of digitalization for sustainability. So think about starting in the agriculture. You bury the sensors on the soil, for water, measuring water, pesticides, whatever you need to have a good harvest. You have a lot of tools in the digitized factory. Even personal planning can be nowadays done. Digital tools, for example. Of course, you have all these online tutorials and so on. You can use it for demand-oriented order planning. I really love that. In car manufacturing, it's totally new that you have the demand of the customer, then you start producing. Having something similar in textile industry would reduce overproduction immediately, and we would create less waste. Not many people know that we have an overproduction of around 30%. If you think about it, how many textiles are treated as a waste from the very beginning? Unbelievable. Yeah, digital printing and things like that, you already know that. But what is coming up is the complete transparency of the value chain with the digital product passport. E-commerce is also something you already know, but we can, for example, use the virtual avatars. You have already maybe seen a picture on that in the previous lecture. So that, for example, in e-commerce, I have really the dresses or the jacket which is fitting to me, and I do not have to send it back. So you can reduce complaints. And yes, of course, all the products which you can use in future with geotextiles, and here we are also in the technical textiles. So here's a picture from Frischler, which is one of the famous carding machine producers, and they are already starting to collect the data for the digital product passport, and they give the data to their customers. And of course, it would be nice, they did not start already, they need to have, for example, an artificial tool which is calculating the data and making maybe some prognostic hints how to use the machine to be more efficient, for example, in energy consumption. What I learned in working in the textile industry, that the systems are very complex and that you can immediately reduce, for example, carbon dioxide emissions, or if you steer the machine in the right way. In a project we have done in Indonesia, together with the textile industry in dyeing and finishing, we found out that with the right usage and the combination steering the machine and new dyes, we had a decrease of consumption in energy of 30 to 40% without any investment, only the time of the people. Yeah, but no machine investment. Of course, the new dyes have a double price, but as you need less, for example, at lower temperature, you can save a lot of energy and heat. So these are things where data are helping us to be more sustainable during the processes. So we have a lot of potential using data and digitalization for greening the industry, but it's only a small intersection, and we have to look very carefully on that, how we use digitalization. because digitalization itself is not sustainable. It's a double-edged sword. Why? The one thing is that digitalization and green transition have different logic behind. Digitalization is used for more efficiency, to create more products, to be cheaper, and think about fast fashion, to create more waste in the end. Overproduction of 30% is only possible with these high digitalization we have already. Think about lean management concepts and so on. The green transition has another logic, and it is thinking about reusing energy. So look at that. We have a lot of opportunities using digitalization for green transition, but mainly it is on the transparency. When we look at digitalization itself, it has a lot of challenges because it has a high increase in carbon dioxide emissions itself. So it uses as much carbon, or creates as much carbon dioxide emissions as in aviation. This is 4%, for example. We have a lot of toxic waste. And it has an impact on the people. We have a huge science or research on how people are affected by this ongoing digitalization, which is called technology express, for example. Yeah, and the green transition is also not that easy. Of course, we have a reduction in carbon dioxide emissions and resources, but it is a real challenge for the people. Think about the designers who are not allowed to use specific dyes anymore. One of the sustainable entrepreneurs in Germany told me that she creates psychological crisis within her designers because she has forbidden to use specific issues, and therefore they have been restricted in their creativity. Yeah, so there's a lot of awareness raising necessary for the common good, and one of the main problems is that the people do not think systemic. They do not think in the planetary boundaries, but only in carbon dioxide emissions, or only in chemistry, or only in biodiversity. And we have to think about all these things together. So we have a high increase in complexity in thinking and steering the industry. So I just wanted to take a deeper look in on the ecological impact. So when we look upstream on these digitalization, the supply chain of digitalization, we have a lot of mining. And if you want to have a dirty industry, then you have mining industry, which needs a lot of chemicals, a lot of water, is destroying the environment and polluting even the society. And it is also changing society. We have one investigation in Indonesia where we see that nickel production is changing the style of living of the indigenous people, for example. So you have to protect minorities, for example. And if you look at only the 2-degree scenario, you see that the demand for lithium, cobalt, and graphite will increase by around 500%. You will see the pressure on our Earth if we use digitalization. So let's think about what we were doing with that. In itself, when we're using digitalization, think about streaming alone. Yeah, we all are using streaming, always online on Wi-Fi. So we are locally increasing the demand very fast. And using artificial intelligence, we have prediction in only Europe that we will have a doubling of the required server power within 4 years. A doubling. Then it will be 8%. And what we have is a huge increase in toxic waste in digitalization. The waste in digitalization is one of the fast-growing ways, and in many chemical and very many technological devices, you are using flame retardants, like in textiles. And to reduce the pops out of the the electronic devices, we have only technology readiness level 5. That means we do not know how to scale it. It's only possible on the laboratory level. So all these things are, of course, as POPs are creating cancer, as mining is destroying society, are of course related to human rights violations, but I don't want to look too deep in the supply chain here. What I want to look at is at the company here, now the company I'm working in, and I am now confronted with more digitalization as ever. Think about the concept which has been introduced by Professor. He wants a continuous monitoring in this data collection. Yeah? So we have already in the laboratories built in some sensors which are collecting water and energy and the other resources continuously. So we exchange you both. You're doing different work, and suddenly the water consumption is changing related to the person which is working there. We could already show in research that there is individual digital footprint in energy consumption. So everyone knows whether you're here or not, what you're doing. You're reading at the computer, are you calculating something, or you're just looking at a phone when you're at work. So you're totally transparent, and so this creates new privacy concerns in this context. If you're totally monitored, it can create new forms of forced labor, because you are in a hierarchical lower position, and you will be under total surveillance, and the people will check about your performance. Artificial intelligence. Think you want to have access, for example, to your laboratory. We know already that a lot of the tools connected, for example, the scanning of faces, will not recognize people of color, or recognize them less than white people, because most of the technology which is designed by white male people. Yeah? It's also discriminating women quite often, and I'm not sure whether this micro is discriminating me a bit, because it may be specified for male voices. Quite often with micros, by the way. So liability of this socio-technical system is something which we know from aviation, that you have these high automation which creates a lot of competences, because the autopilot takes over and the pilot loses competences, or that in specific contexts the people in chemistry forget about how to use the dyes in the right way, because everything has gone to the machine. This is a real problem we have to deal with. We know enough from aviation to transform that in the normal industry and saying, okay, we need to train and retrain the people again and again and again. Huh? Every pilot has his simulations where he trains how to deal with a crash, for example, how to deal with disturbance. People have already lost the capacity, the competency to read cars because of GPS systems. In case of a flood, when all the electricity is gone, then you have a problem if the people who should help you cannot read cards. It was something what happened in Germany. Then we have, of course, the many people working together. Who has designed the product? who is then in the end reliable for the product. We have that already in software management. And of course we have safety and security problems, and I would replace the password here for the Wi-Fi. It's not secure. Please think about that we need some basic knowledge to prevent us against cyber attacks. And of course we have these mental issues, the high mental workload, or maybe also the fatigue if you're not allowed to do anything and you're only in the surveillance. So we have to deal with new topics of occupational safety and health. Yeah, with all these things, we are talking about corporate digital responsibility and some new forms of compliance management and human factors. So I question you again, how is screening of this data possible? I think there are huge opportunities, but we should be very responsible with all that. Some of the colleagues have already invented things, so there are some value-based approaches, and one of that is the ISO EIE standard 7000, which is related to value-based engineering. Every technology is based on values. You think we are rational, but we are developing the technology to make things more efficient, or to support people, to monitor the health, for example. So there are always some values related. And we should always think why we are designing specific products and how we integrate values in that. And so we have the concept exploration stage and development stage. And especially in artificial intelligence, you should integrate the stakeholders from the very beginning. We had already in software engineering the human-centered design approach, but now it is extended to the human rights values, which you should integrate, and you try then to make your first draft on the technology on paper with your knowledge, scratching that, discussing that again and again with your stakeholders, and then trying to make a feasibility study. Is it possible to integrate it in that way as I want it? Make your a risk assessment. Do I have any human rights violation, for example, with surveillance, or do I have a bias that specific people are excluded or not treated well? And then with that concept exploration stage, then you get in the development stage, and you have to build up then a continuous monitoring whether these goals and targets which you have defined are really met. So you have a transparency management process included. This is information management. Although here are already some ISO norms given on that which you can include here. Another approach is the corporate digital responsibility, which is talking about that management has to do a so-called LC assessment, E for ethical, L for legal, S for social implications. So ethical, legal, social implications are LC assessment. You have to do that regularly. Normally, if you invent new products in Europe, you need some digital governance. If there is a corruption from the system, you have to report to the government and to your stakeholders, for example. You have to check with automated systems, is there accountability of your tools, and as a company you have something like a digital strategy. We have to think about the workplaces, occupational safety and health, the ecological footprint, and maybe even on society, think about how social media have transformed our societies, how much hate and how much, how much our democracy is affected nowadays by social media. So also that can be part of your business model. Maybe not in textile. So when we are now introducing more and more technology as artificial intelligence, this will affect us people, it will affect the society, and so there should be something like a just transition process that when people are losing their work because they are not trained workers, then you have to skill them up because they will lose their workplaces, and if you don't train them, they will end up in poverty. So we have really to rethink how we do the transformation process in our company, but also how it affects the environment around. This, in my mind, I have applied for a project at the DAAD, where we said we have to build up new transformation management in the organization. People who know how to deal with the twin transition, to think that sustainability and digitalization together. And it is financed by the German Academic Exchange Service, and we are working together with 2 Indonesian universities. We want to develop open educational resources, which means that should be available in India, of course, and it is also our wish to integrate, of course, researchers of India to these open educational resources, that they show their expertise and their best practices, which they already have in twin transition, and to integrate it in these competence development. The idea is that we need these new competences to deal with artificial intelligence, for example, digitalization, that it is integrated in a way that human rights due diligence approaches are addressed, and that not additional non-ecological impact is created, that we know how to deal with cybersecurity and understand also the limitation of artificial intelligence. And you have to look at compliance too, because there are fast evolving international standards, and so the twin transition framework is take digitalization and the green transition, circular economy, digital product, passport of the regulations in the middle. Understand that there is a huge change management process where you have to integrate the people, where you have to understand how to deal with stakeholders, how to address their needs, and also to create the right work system and the machine itself, the interfaces with the people, that they know how to steer the machine itself, and that you not create additional mental load. This is integrated in the idea of just transition, and of course uses a lot of knowledge from the cybersecurity. We will not look upstream and downstream, only scratch at the surface, that the people know that we are connected in a supply chain. And this is very interesting challenge of the future, how to connect the data, the different companies, because it's not to share the data. If we want to have availability of data, we have to work together and to make highest use of it. So our concept will be that I start from the bottom. We have some management skills to give a rough overview and train change management skills. Then we have maybe the responsible digital business models. Professor Bastian will talk about that. We will talk about inclusive technologies addressing human rights needs. We will talk about EU Green Deal and circularity, which is the future, and of course the impact of climate change. And all these together should create a personal leader in the organization who is not an expert, but who knows what is coming up, and where to integrate the expert at the right position and to manage them that they can work together. That is the idea behind this transformation, management and twin transition. Thank you for your attention, and I hope you have a nice program.
Sorry. Are there any questions? But they took so long, so much of your time.
During lunchtime.
Okay, yeah, that's a good idea. Yeah, thank you.
Thank you, ma'am. Thank you for the nice presentation and your valuable time. So moving to the last presentation of this technical session, our very own director, sir, Professor V.K. Gandha, will be talking on textile structural composites using advanced woven architecture. So please.
Okay, so good afternoon and good before lunch. I think we can continue 30 minutes more. I hope the high caloric kachori may help you. Before I start, couple of things. Because of our tight schedule, we could not devote time for question and answer. Those who are interested to ask any question to any speaker, we may interact during lunch time, even after the day. I mean, all the speakers, they will be with us
in the evening also. So after the conference also you can interact. Faculty members, those who wants to collaborate with Professor Manika and Professor Bastian, you must have heard their lecture, particularly in sustainability and AI. Please contact them, especially request management faculty and computer science faculty. And after this lecture, we will take 2 minutes more to sign one MOU with German University. So please, after the lecture, don't go out. Please stay back. Only 2 to 3 minutes. Okay. So subject is engineering design and application of advanced multifunctional textile structural composites. So in this, the word structural means load bearing. So we developed a composite which can really take load. That is what the concept. And all these structures which I will discuss, they are predominantly woven structures. Before I go to the actual woven structures, let us have a look to some preliminary things, because majority of the audience are undergraduate students. So they should know first what exactly the composite is. If you look at the journey of composite manufacturing, composites exist in nature, as you can see here. Wood and bone, they are composite material. Then man-made composite manufacturing started using different polymer or polymeric substances. Then we developed fiber-reinforced composites. Filament winding is one of the composite manufacturing process nowadays being used for many advanced applications. And nowadays, a lot of research is going on in the field of textile structural composites. So I said, as please remember, whenever I be using the term structural word means load bearing. So what are those structures? Little bit more to history of the composite material. This is the time scale of composite advancements. So composite is nothing new. It's almost 4,500 years old material, as you can see in the picture. The straw and mud bricks, even today, it is being used in rural areas to make the houses in the villages. And gradually the development took place. Today we are producing the composites which are being used to make aircrafts, marine ships, wind turbine blades, and many more advanced materials. As far as our subject is concerned, I will be discussing some of the structures mentioned here, not all, because the time is only 30 minutes. Maybe I will be able to cover 3 or 4 structures in this, but in our research lab, we have developed all these structures to produce composite material, and as I said, all these structures are woven products. So, question is, what are the special characteristics of the composite material and why we do produce composites? So composites, as you can see this stress strain diagram, it's typically, this diagram consists of a linear elastic region followed by a non-linear region with potential carbon matrix debonding, and finally the material collapse. The shape of the curve doesn't remain same every time. The shape of the curve depends predominantly on 3 factors. Number 1 is what is the orientation of the fibers or yarn in the composite structure. Number 2, fiber beam fraction, means in the composite, which consists of a fiber and matrix, what is the percentage of the fibers in the composite, that will decide what is the shape of this curve. And third thing is matrix properties because wide range of metrics are available to make these composites. The whole idea of making composite is the first requirement or the first objective of making composite means we want to develop lightweight structures. Whenever we use some metallic substances, the component or the machine or the tools becomes too heavy. If you want to reduce its weight, then we have to develop a composite material. So lightweight is the first objective. Second objective is some mechanical properties. In this process, we try to develop material which has excellent mechanical properties in terms of its strength to weight ratio or mechanical properties in the composite simply by manipulation of structural variables, their components, and many other factors. Of course, last but the least advantage of composite is particularly when you try to substitute metals, all composites are corrosion resistant materials. So that is another benefit. Then, before I go to my topic, I will tell you the third thing which is very important in the context of today's presentation. What is a functional composite or multifunctional composite? As I said, composite is developed purely to achieve three things: lightweight, excellent mechanical properties, and third is corrosion resistance. Is it enough for various application of composite? Of course it is not. Now we are developing different composite materials which gives you additional properties. Means apart from these three basic things, you can have many other properties. If you can have many other properties, we call it multifunctional composite material. These functionalities can be broadly divided into two types. One is structural function, another is non-structural function. Means some amount of structural functions can be introduced or some amount of non-functional properties also can be introduced to the composite materials. Structural functions include strength, stiffness, stability, and so on. Non-structural functions means energy harvesting, self-healing, sensing, actuation. These are non-structural functions. Both can be introduced. So this is what the basic information you need to understand before I proceed to my presentation. The presentation includes what is global composite industry today, what we mean by advanced textile structures for composites, then different types of structures. Structures include honeycomb, profile, objective, or maybe structural bar composite, ductile composite, additive manufacturing, acoustic composites, and many more. I will try to, whatever, once the time is over, I will stop. I will not be able to complete everything. Let us see how much we can cover. So, first, what is the concept of composite industry, particularly in the developed world? The basic concept of composite today is it must be or it should be essentially a fiber reinforced structure. Although without fiber also we can make composite, simply adding two different polymers. But today, since we are talking of structural composite, the fiber reinforcement has become important so that it can impact necessary mechanical properties to the material. It's a highly knowledgeable industry, means if you want to develop this product, lot of research information, data, and knowledge is required. Most R&D based technical textile you can make without just by experience or just from the basic information. Traditional textiles like suiting, satin, dhotis, uniforms, saris, etc. But not the composite, the form. You need lot of R&D information to make this. Then, to develop composite material of requisite mechanical performance, what you need to understand a detailed knowledge of modeling and simulation. That means lot of mathematical globe. The development in structural composite is still at its infancy, means a lot of research is necessary to really reach saturation status. That is what the position. If you look at the market, there is a tremendous market as far as composite is required. This is a market position shown in global level. Today, the composite material market is 40 billion around, and which is expected to reach about 114 billion. You have to understand one more point before I proceed with my presentation. Remember, composite is just a material, it's not a product. Just like when you talk about developing textile fabric, the basic material is yarn. From yarn we produce fabric. The composite is a material which can be used for different purposes, to make aeroplane body, to make automobiles, or to make wind turbine blade, or any sports items. So composite is a material. So market for composite material and market for composite based products are different. You can see composite market product is much higher than the material. The reason being, there is a lot of value addition over the raw material. Raw material being the composite material. So the forecast is this material will gain a tremendous potential in international market, not only in India, although the growth rate in India as of today is very high. The reason being not that we are giving a lot of emphasis to composite manufacturing, the reason being our base at present is very low. So whatever we are trying, it gives the high rate of, or the pace of development is very high. What are the different growth drivers of composite in India today? Particularly, you must have heard in the morning, aerospace, our chief guest today told India is one of the biggest producer of user of aircrafts, because so many airports in this country nowadays. So aerospace, drone, defense and automotive industry, railway, marine, these are the major markets where it will be used. Corrosion and chemical resistance materials, particularly in construction of pipes and tanks. Electrical resistivity and flame retardant materials, that is electrical and electronic industry. Structural materials, machine components and construction industry, and structural power composite. I will give you a little bit information about this one, that is, which is now we foresee that this material can be used to, is a good material for e-vehicles and drones. These are some of the application areas where composites are being used. The pictures are self-explanatory. And if you look at what is the emerging trend today, which has a direct impact on the composite manufacturing of composite sector, development of low-cost carbon fiber is very important, because for very high-end applications of the composite, we need carbon fiber, but carbon fiber, as you know, is very expensive. It's 10 times costlier, or maybe 15 times costlier than glass fiber. High performance glass fiber also, although the 80% of the world composites being produced using glass fiber, but in India particularly, we don't have a very high quality glass fiber production. We need glass fiber of a very high quality. Then rapid cure resin system. This is very difficult for undergraduate students to understand unless you know how the composite is being produced. You see, the resin curing time really is one of the challenges in producing these kind of materials. Next one, I want to give you idea about objective open composites. First, you must understand what is objective. The material which gives you negative Poisson's ratio is the objective material. So you all understand what is Poisson's ratio. Lateral strain over longitudinal strain is defined as Poisson's ratio. If this Poisson's ratio can be made negative, that means you develop objective material. So what is this negative Poisson's ratio? Normally, if you stretch any fabric or any material in one direction, you can find in the transverse direction it gets contracted. But in objective material, it's reversed. If you are extending in one direction, the transverse direction also gets extended. That's the beauty of this structure, and that gives you objective material. We have several objective structures exist in the nature. From weaving point of view, we have tried to classify these object structure into these four groups. First one is re-entrance structure, which can be produced by knitting and weaving. Second one is foldable structures, which can be again produced by knitting and weaving. Third one is rotating structure, it can also be produced by knitting and weaving. Fourth one is spiral structure. I will give you only one example, and one example is why it gets negative structure, then you can probably understand the rest of the structures. Let us take one example, which is called rotating square. So this is the object structure. How will you know this is the object structure? You just take one unit cell of this rotating square. The one unit cell is this. You try to extend this unit cell in any direction. Let each dimension of the side is x, which is represented here in this trigonometric equation, x and y. When this structure gets extended in x direction, what happens? This is extended one. X becomes del x, y becomes del y, and our Poisson's ratio definition is lateral strain over longitudinal strain. You measure the strain in x-axis and y-axis, take the ratio, you will find this Poisson's ratio value is -1, means a negative value. So any material which gives negative Poisson's ratio is an oxidized material, and this material has a lot of beautiful or excellent properties which I will show you in subsequent slides. Using this principle, we have tried to develop many woven construction from these object structures, and we tried to develop the fabric, tried to measure its Poisson's ratio. You can see the three typical examples here. In all three cases, the stress strain diagram, the x-axis is axial strain and y-axis is Poisson's ratio. In all the three cases, you get the Poisson's ratio is negative. Okay, this is the beauty. The question is, what is the research then in this? If there are some geometry exists, then you can use those geometry to reduce object fabric. Then what is the research component in this? The question is, for different applications, we need this negative Poisson's ratio of different values. How to develop a material which will give you a desired value of negative Poisson's ratio? For example, I want to produce a fabric which must give -3.2 Poisson's ratio. How to develop this? Then you have to understand the engineering of this fabric in terms of its geometry. To do this, we have tried to develop a model. This model shows taking a foldable structure, as you can see here, this is the foldable structure. Then we have tried to, this is a structure or the geometry which is developed by us, the original geometry. One of the PhD students has developed this, and it is also patented. When we try to extend this structure in its vertical direction, then in the original you try to find out what is the side dimension x and y, then find out x dash and y dash, then to find out axial strain, which is simply L dash minus L over L dash, that is strain in axial direction. Similarly, you extend the structure in other direction, from where you will get transverse strain. You take the ratio of axial strain to transverse strain, find out the value of Poisson's ratio, which is a negative quantity. So the conclusion is, if you know how to develop this geometry or new geometry to produce a new or a desired negative Poisson's ratio, it can fulfill many applications. That is what the research component in this. And once you know to this, rest of the things are very simple. This is the sequence. How can you take this geometry? You can make a fabric. Once you know the geometry, as you know, textile students know how to make even a very complex geometry with a fabric simply by using Jacob mechanism. So you take the flower, you take the leaf, you take any complex design, you put it into CAD system. You can find out what will be the weave design using any commercial standard CAD available in the market. So this is what's shown in the different steps. Take the picture, take the apply CAD, and try to find out what will be the weaving construction particulars. Then you make this fabric, then convert it to composite, and try to test this composite for its for its Poisson's ratio, and you will get the value that is gives you negative Poisson's ratio. This is, of course, for BTech students to understand how to calculate Poisson's ratio. Look at this diagram. The piece of fabric taken, you first mark 4 points, 2 points in axial, 2 points in transverse direction. Then you go on extending this fabric, you will find the shifting of these 4 points in different new positions, from where you can find out L dash minus L over L dash. Similarly, in transverse direction, and from where you can find out Poisson's ratio, that is lateral strain over traditional strain. These fabrics have been taken, we have developed this. In weaving, one can also change this negative Poisson's ratio by manipulating two other parameters. One is thread density, effect of thread density on fabric objectivity. That also leads to change the objectivity. Also, the float length. If you change the float length, that also changes objectivity. Need little bit time to understand, but shortcut of time, maybe sometimes later I will explain this. So what are the special properties of these materials? Once you make a objective fabric or objective composite, you will find these properties exist. Object material gives several excellent mechanical properties in terms of energy absorption, shear stiffness, indentation, resistance, synclastic behavior. The diagram is very self-explanatory because to explain these properties needs time. Variable permeability. Using this behavior, you can produce smart filter, high fracture toughness, and these materials are being used in a lot of defense applications because of its protective properties. So these are some of the materials. Look at the first one, blast resistance vehicle. When the defense vehicle just pass over a bomb which is kept inside the soil, if there is a blast, the vehicle can be saved. The people who are in the vehicle, they can be saved because the platform on the bottom is objective material which can absorb a lot of blast energy. So these are some of the applications where objective composite materials are being used. And there are also several challenges. Let me skip it. I only this one, then we will complete others. There is no time. Look at this. This is another interesting area. Of course, at this very initial stage, textile structural power composite. What we do here is we try to develop supercapacitor. So structural power composite means we use two fabrics. One is carbon fabric, which acts as an electrode, glass fabric at the center, which is a separator. What is the concept is we try to mix up mechanical strength with electrical strength. As you know, a battery, the mechanical efficiency is 0, electrical efficiency is full, 1. If you take the example of some structure where the mechanical efficiency is full, electrical efficiency is 0. If you combine these two, if you know how to optimize these two parameters, you can find a new material which will give you a material which can store energy. We call it capacitor or supercapacitor. The concept is you take, this is the structure, the top and bottom is carbon fiber. You can see the next diagram very clearly. Top and bottom carbon fabric, center glass fabric. You dip this fabric in a electrolyte, which is electrolyte means it is basically resin mixed with some electrolyte. It helps to transfer ions through the structure and you can improve the capacitance value in terms of Farad. So this is the basic concept, and because I want to skip the detailed discussion, after developing this material, you can test it. I will show you what test we carry out after developing this material. You can improve the electric energy density of this material simply by surface functionalization. You can treat this carbon fiber with some zinc nanorods or other nanomaterials so that the surface activation takes place, you can get enhanced specific capacitance in your finished product. This capacitor, after development, is characterized by a curve. It's called electromechanical characterization of structural supercapacitor. So in the x-axis is voltage, in the y-axis is capacitance value, and look at this diagram which looks like a hysteresis diagram. Initially the blue one is the original material. If you go on surface functionalization using some nanorods on the electrode, then that hysteresis curve gets enlarged. That means the energy density has increased, the capacitance value is increased. There are several challenges in this research, and I'm skipping it, but definitely you must look at what are the reasons to develop these materials. These materials can be used to electric vehicles, to drones, many electrical applications. Even defense people also trying to develop these materials to make jet aircrafts. Okay, I will skip this, please, because time is getting delayed, and there is additive manufacturing. We have a lecture in the afternoon on detailed this. I particularly, all BTech students, please be here to listen this lecture on additive manufacturing. You get good knowledge in 3D printing, how it is helping to develop functional composite material. Please attend this lecture. Okay, even we have developed acoustic composite material. This is very, very interesting. Recently we have completed a PhD project on this. We have developed different textile structures which can be used after converting into composite material as an acoustic composite material. It's a very new field, also quite interesting. Okay, what is outlook of this field? See, lightweight engineering. When I am saying lightweight engineering, it basically detects composite material. In some countries, like in Germany, there is an institute for lightweight engineering institute in Dresden, and several in Japan or in some developed countries. They basically work on composite. The department is called lightweight engineering because, as I said, one of the major objectives to develop composite material is to make the material lighter, so that we get use less energy. We want carbon-free environment. It's a really sustainable research. The growth drivers, particularly in India, is transportation industry, that is lightweight. You can see Indian trains are very, very traditional. No change has taken place in the last 50 years. They are very, very heavy trains. If you go to Japan, you will see bullet trains, so lightweight, runs at 400 kilometers per hour. So if you want to run your train at a low high speed, you have to reduce the weight. Very simple logic. For example, all these e-cars nowadays coming up in a very big way in this country. If you want to make effective e-vehicles, you have to reduce weight. And one of the major ways to reduce weight is simply substitute metals by the composite material. That is what the process. So in construction industry, also in objective composite, I have already told you, these are some of the major growth drivers of these industries. There are several challenges, particularly in India. As I said, to make composite, we need a lot of high performance fibers. This country lacks to produce high performance fibers. Even the glass fiber, which is the cheapest high performance fiber, we don't have facility to produce high quality glass fiber also. You forget about carbon, you forget about aramid, you forget about, nylon 66, even basalt. No high performance fiber is being produced in this country. That's another challenge. And cost reduction in 3D fabric production, I have already told you, we don't have any commercial 3D weaving machine in this country. We need to develop that. Also, commercial 3D weaving machines means which can produce the fabric at a high speed. The machines which I have told, which is being developed, the speed maximum you can get it maybe 30 picks per minute only, or 50 picks per minute. We need to develop a machine which can run at least 200 picks per minute. Then only this process will be viable. And last but not the least, processing skill. Composite does not only need mathematical equations or modeling knowledge, it also needs skill, means how to convert reform into composite material. what should be the technical skill to infuse resin effectively. You did a lot of practice and experience. That is what we end of this story. Now I request Dr. Jamini.
Thank you, sir, for the comprehensive yet quick presentation of yours. So now moving ahead with today's program, another milestone we all are about to witness is signing a memorandum of understanding between the Technological Institute of Textile and Sciences, Bhiwani, and Hochschule Niederwehr University of Applied Sciences. The MOU will surely serve as a roadmap for knowledge dissemination, technology transfer, student-faculty exchange program, and hence collaborative research and development endeavors of both the stakeholders involved. May I now invite Professor B.K. Behra, Director TIT&S Bhiwani, and Professor Joost Schutter of Hochschule Niederwehr University of Applied Sciences to sign the MOU. Please, sir.
Daksha. More left. Dipan.
Can we have a big round of applause? Thank you, sir. Now I invite our chief guest, Mr. Malhotra, Director Sir, all the overseas and national speakers, delegates, all the faculty colleagues and students for lunch at Boys Hostel Mess. So another humble request is that since we are running short of time, all the participants are requested to be back here within half an hour, that is by 2:45. As the third technical